This work is part of MFMET for establishing metrology standards in microfluidic devices, a European project financed by EMPRR. I'm Hua Bingying from University of Glasgow, and I'm going to talk about measuring the dimensions of microfluidic devices using optical methods. As you might have heard from previous speakers, typical microfluidic devices have channels of tens of microns. These dimensions are comparable to the size of biological cells. Consequently, microfluidics has found numerous applications in biological analysis. For example, microfluidics has been used for cell sorting, total cell analysis, studying bacterial response to antibiotic resistance, or generate droplet-based bioreactors. In all these applications, manipulating cells and flows within microfluidic devices depend on their geometrical characteristics. To develop microfluidic devices for any application, it typically involves designing, fabricating, and characterizing the devices. By designing the channel width, height, and length, we can modulate hydrodynamic resistance of a microchannel and consequently its flow characteristics. The equations here describe the relationship between the device dimensions, hydrodynamic resistance, and pressure. Once the design is finalized, a range of methods can be used for device fabrication. Microfabrication typically involves multi-stage processes, while practical variations are unavoidable. Therefore, it is crucial to characterize the fabricated devices to identify any discrepancies and prevent compromised performance. To characterize the dimensions of a microfluidic device, we need to choose an appropriate tool. For instance, while a ruler with millimeter units is sufficient for measuring a person's height, it lacks precision for microfluidic channels. In such cases, an instrument capable of resolving features at the micron level is necessary. Among a range of well-established methods for measuring dimensions, optical microscopic technologies have particular advantage for measuring enclosed microfluidic devices, as they don't require physical contact with the surface. This seminar will elaborate some of these technologies using transfer standard chips as examples. Each design of the transfer standard chips includes main channels and a leakage channel in between, with the length of the channels in millimeter, but the dimensions of the leakage channels in microns. I will compare several commonly used optical instruments for measuring these dimensions. Optic microscopes are often used together with microfluidic devices. Optic images have different pixel counts depending on instrument settings. Therefore, a reference, also known as a scale bar, is used to convert pixels to microns. This process can be easily done using open software such as ImageJ. Next, it is crucial to consider the uncertainties associated with each measurement. Typically, there are two largest sources of uncertainties. One stems from the instrument itself. This can be calibrated. Use a standard scale bar to determine errors in measuring the reference length. The other source of uncertainty relates to actual measurements and consists of standard deviation derived from repeated measurements. The standard uncertainty for each measurement is quadratic sum of these two as described here. Since the diameters of hole and the channel width are of hundreds of microns, they can be measured in a single image. To determine the width, it is necessary to identify the outermost edges of a channel and then measure the distance between these edges. To measure the diameter of the holes, the internal boundaries of the hole must be identified. As you would appreciate, the uncertainties exist regarding the precise location of these boundaries. However, to measure the total length of the channels, tiled images are required. The total number of frames needed depends on the field of view of the instrument. The accuracy of measurement is also affected by how the frames are stitched together and the image quality. I will elaborate this using 3 instruments. The first instrument is a Nikon D5300 digital camera, known for its large field of view. It requires only 2 frames to cover a 40 mm long channel. To stitch frames, images must be taken with overlapped areas. Common features such as a blemish can be used to align the frames. An example of this is illustrated here, showing a misalignment of 10 pixels between 2 frames, giving a clearly visible gap. With a stitched images of entire device, the total length of the channels can be measured. However, determining the endpoint of the channel is affected by the image quality. For example, images taken with Nikon digital camera often have relatively poor quality with the leakage channel barely visible. This gives high uncertainty. Images taken with Leica stereo microscope offer improved spatial resolution and contrast, which reduce the measurement uncertainty. The third instrument is a Zeiss axial image with a motorized stage. The stage precision is less than 1 micron, making the stitcher between frames indistinguishable. Furthermore, the high clarity of these images allow easy identifying the boundaries, result in very low uncertainty. While all these 2-dimensional images contain 3D information, they lack Z-axis resolution, so that they are not suitable for measure depth of the channel. To measure the depth of internal microfluidic channels, confocal microscopy is a promising method. Confocal microscopy operates on the principle of confocality, which eliminates autofocus fluorescence light from focal planes. This process is also known as optical sectioning. By collecting a series of optical sections in Z-axis, confocal microscopy can produce 3-dimensional images. The achievable resolution in the Z-axis depends on the numerical aperture of the objective lens. Higher NA objective lens enables thinner optical section. The image here shows a Z-stack of 180 optical slides captured with 100 times NA 1.3 objective lens and their corresponding fluorescence profiles at each Z distance. To estimate the channel height, we must identify the start and end slice for the channels. Due to imperfect confocality, a decision has to be made regarding the threshold of fluorescence intensity. For example, we can use 1% intensity of that at the channel's middle height as a threshold to determine the start and the end slices. Obviously, this arbitrary approach introduces uncertainties. Therefore, height measurements of enclosed microfluidic channels often have larger errors compared with the length and width measurements. We'd like to thank all the members in the project team. You can find more information in the links in the video description and on the project's website, mfmet.eu. With this, I would like to end my presentation. Thanks for watching.